Hello everyone, my name is Felisa from SMA to IPA, and in this video, I will be teaching some basic lessons about latent heat. In this discussion, I will divide it into 4 content. First, what is latent heat, and including the demonstration of latent heat to better understanding about latent heat. Second is the types of latent heat, including the graphic and the formula of latent heat. Third is table of latent heat and the specific heat capacity. And the last is problem solving of latent heat. First, what is latent heat? Latent heat is the energy released or absorbed by a substance during a change of state without a change in its temperature. For example, imagine we have taken some ice in a container. And let's say the ice is supposed at the temperature of negative 17 degrees Celsius. Now, we provide some heat to the ice so that its temperature rises to 0 degrees Celsius. Until now, the ice is still in solid form. The heat given to raise the temperature of ice is known as sensible heat. So we do know now that sensible heat is the heat given to raise the temperature of a substance. Now, if we further heat the ice at 0 degrees Celsius, then the ice will start to melt. This heat is known as latent heat. Thus, latent heat is the quantity of heat absorbed or released by a substance undergoing the change of state. For example, ice changing to liquid or liquid changing to ice at constant temperature and pressure. Because we already learned the basic way of latent heat, let's learn more detail and the specific way of latent heat. Suppose there is solid material in a container whose atoms are shown here. In solid, the relative distance between the atoms is very small. This is the reason there is very high force attraction among the molecule. The small particle of solid always vibrate about their main position. But when we provide energy to it, it will start to vibrate fast. When the temperature reaches the melting point, particles start to vibrate fast and the structure becomes unstable. After the temperature has reached the melting point, and if we provide more heat to it, it will start to melt. The heat added at the melting point of solid substance to change its phase known as latent heat. After raising the temperature of liquid to its boiling point, and if we further provide heat, it will start converting into vapor phase. Energy provided, which is latent heat, required to change the liquid phase into vapor phase. After boiling, distance between the atom amplifies very high. This kind of arrangement is in gaseous state. Now, in the end, we can conclude that latent heat is a form energy which is needed whenever there is a phase change. Like in here, solid to liquid there is a phase change, and liquid to vapor there is a phase change. And there is no phase such temperature rise in latent heat, where like sensible heat, there is temperature rise. Because we already learned the definition of latent heat, let's learn the types of latent heat. There's 2 types of latent heat. First is latent heat of fusion. Latent heat of fusion is the amount of thermal energy required to change a substance from solid state to liquid state without a change in temperature. For example, ice cube melting as their temperature rises. During melting, the ice absorbs latent heat, which is used to change the state of water from ice to liquid water. While the ice is absorbing latent heat, its temperature is not changing. Second type is latent heat of vaporization. Latent heat of vaporization is the amount of thermal energy required to change a substance from liquid state to gas state without a change in temperature. For example, when a pot of water is kept boiling, the temperature remains at 100 degrees Celsius until the last drop evaporates. Because all the heat being added to the liquid is absorbed as latent heat of vaporization and carried away by the escaping vapor molecule. Next is the graph of latent heat. Here we can see there is a horizontal line and a vertical line. Horizontal line is where the heat supplied and the vertical line is where the temperature rises. Here there is a line that slightly tilted up. The line slightly tilted up means there is a heat supplied and there is a temperature rises. Remember, this phase is still in solid phase. And the formula is Q, which is the amount of heat absorbed or released, equal to M, the mass, C, the specific heat capacity, times the delta T, change in temperature. After that, we came across to the straight line. The straight horizontal line, which means there is no temperature rises, but there is a heat supply. The formula for this is M, mass, times LF, the latent heat. After that, we can see the line is slightly tilted up again, which means there is a heat supplied and there is a temperature rises. The formula is the same as the solid phase, which is the MC times delta T. After that, we can see that the line is straight again. The line is straight again because there is no temperature rises, but there is a heat supplied, which is the latent heat of vaporization. The formula for this is the same as the latent heat of fusion, which is M times LV, or latent heat of vaporization. After that, we can see that the line is slightly tilted up again, which means there is a heat supplied and there is a temperature rises. The formula for this is the same, M times C times delta T. Remember, it's still in a gas phase. Next is the table of latent heat and the table specific heat capacity. First, I will explain the table of latent heat. In here, the table is divided into 5 columns. First column is the substance. Second column is the latent heat of fusion, where the unit is in kilojoule per kilogram. Third column is in Celsius, which is the melting point. Fourth column is the latent heat of vaporization, same as the latent heat of fusion, where the unit is kilojoule per kilogram. And the last column is the boiling point. Next is the table of specific heat capacity, which defines as the amount of heat required to raise the temperature of 1 kilogram of a substance. There is 3 columns here. First is substance. Second column is the heat capacity, but in joule per kilogram Celsius. The third column is the heat capacity, but in calorie per gram Celsius. Now, because we already learned what is latent heat, the types of latent heat, the graph of latent heat, and last, the table of latent heat, let's proceed into the problem solving. First problem solving. A 5 kg acetic acid at 5 degrees Celsius is exposed to heat until reaching a temperature of 20 degrees Celsius. How much total BTU of energy will be required in order to reach that temperature? First, let's write the given. The given is the mass is 5 kg. The initial temperature is 5 Celsius and the final temperature is at 20 degrees Celsius. It is asked how much total energy in BTU. To solve this, first let's draw the graph. Where the horizontal graph is the heat supplied and the vertical graph is the where temperature rises. And it said the initial temperature is 5 Celsius, so it should be below here. And the final temperature is 20 degrees Celsius, so it should above 5 degrees Celsius. After that, we should know when will it melt and when will it boil, and the specific heat capacity and the latent heat fusion. So let's go to the table of latent heat and the specific heat capacity. This is the table of latent heat. it is said the acetic acid, so the latent heat of fusion is 192, and the melting point is 17 degrees Celsius. Latent heat of vaporization is 395, and the boiling point is at 118 degrees Celsius. But we don't need latent heat of vaporization because in the question it is only until 30 degrees Celsius. After that, let's search the specific heat capacity of acetic acid, which is the specific heat is 2180 joule per kilogram Celsius. So let's go back to the slide where we left earlier. Because we already know the melting point and the boiling point, let's put into the graph. The melting point is at 70 degrees Celsius and the boiling point is at 118 degrees Celsius. And don't forget the specific heat capacity, which is 2180, and the latent heat of fusion is 192,000 joule per kilogram. After that, let's connect the line 5 Celsius to 118 degrees Celsius. Because the melting point is at 17 degrees Celsius, so 5 to 17 degrees Celsius, it should be go up right here. And then 17 degrees Celsius is the melting point, so it will go straight. And 17 degrees Celsius until 118 is the temperature rises. After that, let's draw some dots into 17 degrees Celsius, 20 degrees Celsius, and 118 degrees Celsius. Because the graph is all done, let's search for the Q total but in BTU. To search Q total is Q1 plus LF plus Q2, which is Q1 is mass times specific heat times delta T, which is the mass is 5 kg, the C is 2180, and the delta T is 17 minus 5, which is 130,800 joule. Next is the LF. LF is M times LF. The M is 5 kg and the LF is 192,000 joule per kilogram, which the result become 960,000 joule. Next is the Q2. The Q2 is mass times C times delta T. The mass is 5, the C is 2180, and the delta T is 20 minus 17, which is, the result is 32,700 joule. After that, let's sum the Q total, where 130,800 joule plus 960,000 joule plus 32,700 joule become 1,123,500 joule. Because it is asked in BTU, so 1 BTU is 1055 joule. So the result of the Q total divided by 1055 joule is 1065 BTU. Next is the last problem solving. A total heat of 118,164 calories is required to increase the temperature of ethyl alcohol from 50 degrees Celsius to 80 degrees Celsius. How many slugs of ethyl alcohol required? First, let's start from the given. The given is the Q total, or the total heat, is 118,164 cal. The initial temperature is 50 degrees Celsius and the final temperature is 80 degrees Celsius. It is asked the mass but in slug. So let's draw the graph. The initial temperature is 50 degrees Celsius and the final temperature is 80 degrees Celsius. So let's go to the table of latent heat and specific heat capacity to search when it will boil or melt, and the specific heat and the latent heat of fusion or vaporization of this. Here is the table of latent heat. Ethyl alcohol is the same as ethanol. The initial temperature is at 50 degrees Celsius and the final temperature is at 80 degrees Celsius. Because the initial temperature is from 50 degrees Celsius, so we don't need the latent heat of fusion because it's from negative 114 Celsius. So we can say that the boiling point is at 17.8 degrees Celsius and the latent heat of vaporization is at 888 kJ per kilogram. Next is the specific heat capacity. Next is the specific heat capacity. The specific heat capacity of the ethyl alcohol is 2428 joule per kilogram Celsius. Because we already know all the information, let's go to the slide where we have left. It is said that 78 Celsius is the boiling point, so it should be above 50 Celsius. And don't forget the specific heat capacity is 2428 and the latent heat of vaporization is 888,000 joule per kilogram. Because we already know all the temperature, let's draw the graph. 50 degrees Celsius to 78 degrees Celsius, the graph should go up because 78 degrees Celsius is the latent heat of vaporization. Because 78 degrees Celsius is the latent heat of vaporization, there should not be changes in temperature. And then 78 degrees Celsius to 80 degrees Celsius, it should go up. Because the graph is all completed, let's search for the mass. To search the mass, let's start from the given. The given is Q total, which is Q1 plus LV plus Q2. The Q total is 118,164 calorie. Because it's set in slug, so the cal should be in joule. 1 cal is 4184 joule. So the result of the Q total is 4678398 joule. After that, let's solve for the mass. Q total is Q1 plus LV plus Q2. The Q total is 4678398 equal to mass times the C 2428 times the delta T 78 minus 50. After that, plus LV, which is M times the C, the LV 838,000 joule per kilogram plus the mass times the C 2428 times the delta T 80 minus 78 will be resulting mass times 2428 times 28 plus 838,000 M plus 4856 M, which will be resulting 910840 M, which the M will be 5 kg. 1 slug is equal to 14.59 kg. So the mass should be 0.3427 slug. Okay, so that's all for the video. Hope you understand the lessons and thank you for watching.